Simon, I will try to beat Simon's time, but I think it's possible.
No, we are okay.
Well, thank you for the opportunity to show you this work. My name is Perković, as you pronounced correctly, and I come from Military Technical Institute from Aeronautical Department, and that's where our troubles come from. Actually, we had a problem with some parts of hydraulic system for the aircraft and the availability of certain steels. So we got a task to change the material for those parts. So we had to find a part that is strong enough, tough enough, available, weldable, and can be maintainable. So it's a bit difficult. So that's why we came up with the duplex steels as a perfect solution for this. And with our help of colleagues, I think we made a good choice. But we have to keep one thing in mind, and that's the damage tolerance principle, which is the main principle for design in the aircraft industry, because we operate in very little tolerances. And in a simple language, that means that we can have a part that has a visible damage, but as long as it performs, we are satisfied with it. So that's why we need to have some kind of material that can maybe have a crack, but that crack has to grow slowly so we can monitor it and keep it under control. So that is why we chose the steel S32750 or 1.4410 according to EM standard. But and we made lots of analysis, and this paper is just the beginning of one of those analyses. So we started with a base material, and the results that you can see here is the chemical composition of the material that we got. Actually, we made all the measurements, and these chemical composition comply with standards. And of course, we measured all the mechanical properties. So these are not generated by the manufacturer. Actually, those mechanical properties are measured in our institute. And you can see what was important for us is the impact toughness, where you can see three values very close to 300. Actually, we got a couple of values a little bit above 300, but our Charpy pendulum is limited to 300 joules, so it did not measure about it. So we cut off those results. Yes, most of the specimens are standard Charpy specimens, as displayed here, and we tested them at the range of temperature starting from the room temperature up to minus 100 degrees. And if you can take a look at these results, actually that's what we expect, that we can get lower and lower energies with the lower temperatures. That's what we accepted. But one thing is important, that crack initiation energy is always lower than crack propagation energy. And that is why we are coming back to the first definition of damage tolerance principle. So to show you how it looks in the diagrams, it's the results that were shown in the table. Actually, we start with the front upper left diagram with the room temperature, and we go at the lower left right the diagram with the minus 100 degrees temperature, and those diagrams show force versus time and the energy versus time. So you can obviously see the decrease in force, and what is the most obvious is decrease in the energy. But again, I repeat, the energy of initiation is always less than the energy of propagation. Now, further tests, what we did is to make a range of specimens and make a pre-crack on the the Rumel's fractal device, and we made cracks starting from the standard notch of 2 millimeters. Then we added cracks, depends, 2 to 5 millimeters range of them, and we then tested them again, but not at the full range of temperatures that we did before, because we were limited with the number of specimens. But we only did at room temperature, -40, -60, and -80. In this case, we then measured the impact and made the diagrams of the impact energy, kV versus crack length. And those diagrams are shown here depending on the temperatures. So you can see the decrease of the kV factor with the growth of the crank length existing in the specimens. From those diagrams, we got the kV band, and that is what we actually wanted to do. Then we compared the kV from the notched specimen, the standard specimen, with the kV1 from the cracked specimen, and we got the crack sensitivity. The values from the crack sensitivity showed us that the crack sensitivity that does not decrease with the lowering of the temperatures. That showed us that the performance of this steel was good enough, and it was a good choice. Although if we make additional comment that the steel also has high impact toughness on low temperatures, considering that usually those aircraft parts are used on high altitudes where the temperature is usually -50 to -55 degrees. So that's the range of the temperatures we are operating in. So this steel is good enough, has high impact values on low temperatures, good enough, and still it has a crack sensitivity, does not lose its value with the lowering the temperature. So then we established a good baseline. So this baseline is now the beginning of the next stage to prove that this steel that's weldable, and to prove that how the welding will influence these same conditions. So this is established as the baseline. We got the green light for the next stage to expand this the whole process with the welding, and to test the welding and the influence of the welding on these materials at low temperatures. So basically, I don't think if I managed to beat the Siemens time, but in short, I try to do my best.
Yeah.
Okay, thank you.